Good morning, students. Myself, Vijay Shankar from ECE Department, Chipro Engineering College. So today we are going to discuss about the concept of convolution in frequency domain. Concept of convolution in frequency domain. Okay, we already know the convolution integral and convolution sum. In this frequency domain, we are using the convolution to find out h of f is equal to the ratio between of the output response to the input response, y of f by the x of f. Let's see the frequency response of linear time invariant system. Linear time invariant system. The linear time system from an important class in the communication. See, till now, last class we discussed about the different types of the classification of the linear time invariant system and the causality and some properties we already discussed. And in this, the linear time systems form an important class in the communication. The amplitude and the phase response, realizability, bandwidth, distortion during the transmission of signal are all very important concepts related to the design and implementation of the system. In any communication system, you have to send any. In that signal, the amplitude is very important and the phase response, realizability, bandwidth, distortion, and during the transmission of a signal. Okay, during the transmission of a signal, you have to see all these parameters and we design the system. The frequency response, here the frequency response of the system gives the of magnitude and the phase of the system. Magnitude and phase of the system output with respect to the frequency on application of the input. We know that the output y of t of the system is given as, see here, this is a formula for the convolution formula. Okay, my dear, formula. So y of t is equal to the x of t convolute with the h of t. Okay, my dear friends. And this y of t, the t is nothing but the continuous time. Continuous time is integral minus infinite to infinite x of tau, h of t minus tau d tau. Because of the convolution obeys the commutative property, we can interchange the values of x and h also. H of tau, x of t minus tau d tau. So both are the correct. AB is equal to B as a commutative property. For continuous, what about the discrete time function? The y of n is equal. N is represented for the discrete. Sum of n is equal to not the n, k is equal to minus infinite to infinite x of k, h of n minus, or is also equal to the sum of equal to minus infinite to infinite h of k, x of n minus k. Okay, the discrete time function as a continuous time function is integral. We are using the continuous time function y of t is equal to integral minus infinite to infinite x of tau h of t minus tau d tau. Okay, this equation gives the time response of the linear time invariant system. I can apply the Fourier transformation on both sides. The RHS of the above equation represents the convolution of the integral x of t. RHS, see in the right hand side. represents the convolution of the input signal x of t and impulse response h of t. By applying the Fourier transformation on both sides, Fourier transformation of y of t and the Fourier transformation of the total function, convolution function. We know the convolution of two functions is transformed into multiplication of their Fourier transform. So according to the convolution in time, let x of t and the h of t, what is the Fourier transformation? Is x of f and the h of f. The product will get. Or otherwise, in terms of the angular frequency, the Fourier transformation is x of omega into h of omega. Okay. So we know that the convolution of the two functions is transformed into multiplication of their Fourier transforms by applying this above equation as the y of t is equal to some k into x of t minus t naught. The y of t is equal to k into x of t minus t naught. Here the k is a constant, represents a change in amplitude, and t naught is a time delay in the transmission of a signal through a system. And by taking the Fourier transformation on both sides of the above equation, so what I have taken here, the y of t is input is delayed with the t naught samples. Input is delayed with the t naught samples. So y of t is equal to, assuming with the coefficient as a k, nothing but the constant represent the change in amplitude. The y of t, the Fourier transformation is y of f, and is a Fourier transformation of the y of t is equal to the Fourier transformation of k into x of t minus t naught. Now, what is the Fourier transformation of the time delay function x of t minus t naught is a Fourier transformation e power minus j omega into t naught, because it is shifted with the t naught samples, x of omega. Or in terms of the frequency, normal frequency, e power minus j 2 pi f into t naught. X of omega is the shortcut notation is x of f. Okay, my dear student. See now the y of f is equal to the Fourier transformation of k into x of t minus t naught as a k x of f e power minus j 2 pi into t naught. This is the equation. Okay. Now cross multiply the y of f and h of f, y of f and x of f, h of equal to y of f by x of f. Bring the RHS in the above equation, the 2.13.4. In the above equation, the h of f is equal to k into, yes, k into e power minus j 2 pi f into t naught. So y of f, h of f, x of f is nothing but h of f. H of f is equal to e power minus j 2 pi f into t naught into k. This equation gives a transfer function for a distortionless system. Distortionless system. Okay, my dear students. It is clear from the above equation that the magnitude of a transfer function is k, which is independent of frequency. That is, the transfer function has constant amplitude at all the frequencies. The phase shift of the above equation is the phase shift. What is the phase shift here? The j coefficient 2 pi f into t naught. Okay, my dear students. So the magnitude is k and the phase shift is a 2 pi f into t naught. In the above equation, the magnitude becomes it is a k value and the phase constant is a 2 pi f into t naught. How? Whenever we consider as z is equal to r into e power minus j theta, theta is a phase constant and r is a magnitude. That is, students. Next one, So the theta f is equal to minus 2 pi f into t naught. That is equal to minus 2 pi t naught f. That is, the phase shift is linearly proportional to the frequency. Linearly proportional to the frequency. Here, the phase shift is linear. Frequencies. This can be expressed with the example of x of t is equal to cos 2 pi f into t. Cos 2 pi f into t minus 2. Now let the output signal be same in the amplitude but shifted in the time by the t naught seconds. Y of t is equal to cos 2 pi f t minus t naught. T minus t naught, time invariant, it is a time variant. This equation can also be written as y of t is equal to cos 2 pi f into t minus 2 pi f into t naught. So what it has a cos 2 pi theta is a cos 2 pi f into t, the 2 pi f t naught, nothing but the theta f minus theta f is there. Okay, my dear students. Minus 2 pi f into t naught is a theta of f value is equal to. Thus, the phase shift y of the theta f is equal to minus 2 pi f into t naught, which is proportional to the frequency. The Fourier transformation of the total function of the convolution is equal to x of f into h of f. Here, h of t is a transfer function of the system. Y of f is equal to h of f into x of f. Thus, for a linear time invariant system, the Fourier transformation of the output signal is equal to the product of the transfer function of the system and the Fourier transform of the input. The above equation gives the frequency response of the system. Frequency response of the system. Okay, my dear students. So actually the distortionless transmission through the system is a distortionless transmission means the output of the system is an exact replica of the input. The difference between the input and output of such system is that first one is amplitude of the output signal may increase. See here, the amplitude of this output signal may increase or decrease by same factor with respect to the input signal. And second point, the output signal may be delayed in the time with respect to the input signal. See, the output signal may be delayed in the time with respect to the input signal because of the system. Therefore, the output signal y of t can be written in terms of the input x of t as So actually here there is no any equation. I will write that one. X of t as what I am saying k into the y of t, the actual function, the y of t is equal to the output function. It is output function. The amplitude of the output signal may increase or the decrease by some factor with respect to the input. So what is the factor here? The k is a factor. And the output signal may be delayed in the time with respect to the input signal because of the system delay. So the output is the input delayed with the t minus the t naught. Therefore, the output signal y of t can be written in terms of the input signal as y of t is equal to k into x of t minus t naught. This is a distortionless transmission, the distortionless transmission through the system equation actually. We already seen here in the above slide, that is a y of t is equal to, the y of t is equal to k into x of t minus t naught. Okay, my dear students, actually that statement will get here itself. I will modify this one. So once again, I will explain my dear students here. A distortionless transmission through a system for the frequency response of a linear time system. The linear time system from an important class in the communication, the amplitude and the phase response, realizability, bandwidth, distortion during the transmission of a signal are all very important concepts related to the design and implementation of the system. That the frequency response. The frequency response of a system gives the variation of magnitude and the phase of the system output with respect to the frequency on application of the input. We know that the output y of t of the system is given as convolution. The y of t is equal to integral minus infinite to infinite x of tau h of t minus tau d tau. This equation gives the time response of the linear invariant system. Now I can apply the Fourier transformation on both sides, y of t and the Fourier transformation of this convolution equation. We know that the convolution of two functions is transformed into the multiplication of their Fourier transforms. By applying this above equation, the Fourier transformation of this equation is x of f and h of f, because the two signals we have, one signal is x and another signal is a h. Here h of f is called a function of the system. H of f is called the transfer function of the system. Therefore, the left hand side Fourier transformation of y of t is y of f, and in the right hand side the Fourier transformation of convolution equation is x of f and the h of f. Thus, for a linear time invariant system, Fourier transform of output is equal to the product of the transform function of the system and Fourier transform of the input. See again, the product of transfer function of the system. Why I am calling it as a transfer function of the system? Transfer function is nothing but output by the input. Here the h of f we can call it as a transfer function. And the Fourier transformation of the input. What is the input here? X. The above equation gives frequency response of the system. Frequency response of the system. Okay, friends. So actually the block diagram looks like this. The x of t is the input signal, and the h of t internally, nothing but is a system it is. That system is a linear time invariant system. Getting the response is a y of t. What is a y of t here? Is equal to the h of t with convolution of h of t. What is the Fourier transformation of y of t? Y of f. And the Fourier transformation of x of t, h of t is x of f into h of f. So what is the h of f? Is a transfer function put by the input. Output is y of x, y of f, my friends, and the input is x of f. Okay, thus the linear time invariant system. This system, linear time invariant system, Fourier transform of output signal y of f is equal to the product of the transfer function of the system h of f and the Fourier transformation of the input signal x of f. The above equation gives the frequency response of the system. Frequency response of the system. Now, in that, a distortionless transmission through the system. Always we need in the transmission, it is always in the distortionless. The transmission is distortionless. Without a distortion, if there is any distortion, the noise is there, that is nothing but one distortion. Amplitude is decreases, that is also one distortion. And the frequency changes, that is also one distortion. Okay, amplitude distortion, frequency distortion. And these type of distortions are avoided during the transmission through the system. Nothing but we can call it distortionless transmission through system. Okay, my dear students. For this, we have to do that. A distortionless transmission means the output of the system is an exact replica of the input signal. That is nothing but the distortionless. Whatever I send here, it is received at the receiver side without any distortion or without any noise is added to the signal. Okay, so one signal is transmitted on the transmitter side. That signal is received at the receiver side. Okay, my dear students. Let here assume there is a transmission, and here the receiver, and it is transmitted a signal from transmission to receiver. It receives at the receiver side without any distortion. Suppose if I am sending that it is a waveform, sinusoidal waveform. Distortionless means same sinusoidal signal you have to get. Distorted means, suppose here the distorted like this. There is a distortion occurs. Without any distortion, exactly the replica, what we send it from the transmitter, it is received at the receiver side. That we can call it as a distortionless, or it is exactly replica what we send from the transmitter. Okay. A distortionless transmission means the output of the system is an exact replica of the input signal. The difference between the input and output of such a system is that the difference between the input and the output for that system, distortionless system, is first one, amplitude of the output signal may increase or the decrease by some factor with respect to the input. What is the output here? Y of t. What is the input here? X of t. And what is an amplitude? Nothing but we can take it as a k. K is either be increasing or decreasing by some factor. Nothing but it's a k value. What is the second point saying that the output of the signal may be delayed in time with respect to the input signal. May be delayed with respect to the input signal because of the system delay. Because of the system delay, the output may be delayed with respect to the input signal. So the output is equal to increase either the decrease of some factor k, and it is a delayed. That is nothing but x of t minus t naught. X of t minus t naught with the t naught samples is delayed. Due to the system delay only, the output signal may be delayed in time with respect to the input signal because of the system delay. Therefore, the output signal y of t can be written in terms of input signal x of t as y of t is equal to k into x of t minus t naught. K into x of t minus t naught. Here, k is constant, represents change in amplitude, and t naught is a time delay in transmission of signal through a system. The time delay in transmission. By taking the Fourier transformation on both sides of the above equation, what is the y of t? The y of f, and k into x of t minus t naught according to the time shift property of the Fourier transform. X of f into e power minus 2 pi f into t naught. It is delayed with the t naught samples. Okay, my dear students. The transfer function h of f is given from the equation h of f is equal to y of f by x of f. Okay, so cross multiply here the y of f by x of f. Substitute the function h of f is equal to k into already the x of f we got here, e power minus j 2 pi f into t naught. Okay, this equation gives the transfer function for a distortionless transmission or the distortionless system. it is clear that from the above equation, the magnitude of the transfer function is k, which is independent of the frequency. Here there is no any frequency, my dear students. Frequency means f is included. There is no any frequency, it is independent of the frequency. That is, the transfer function has constant amplitude at all the frequencies. There is no any change in the amplitude because it is independent of the frequency. But the phase shift above equation, see here, the phase shift is depends upon the frequency. Pi of f or the theta of f is equal to the coefficient of J here. Theta of f is equal to minus 2 pi f into T naught, or minus 2 pi into T naught into f. See the f here. So it is depends upon the frequency. That is, the phase shift is linearly proportional to the frequency. Here the phase shift is linear for all the frequencies. This can be expressed with the example of, that example is, let there be a signal in the time domain as x of t is equal to cosine function. Let the output of signal be same as the amplitude, but it is shifted in the time t naught samples. Y of t is equal to cos 2 pi f into t minus t naught due to the system delay. This equation can also be written as y of t is equal to cos 2 pi f into t minus 2 pi f t naught. What is a minus 2 pi f into t naught? Is a theta f. Theta of f. Thus, the phase shift of y of t is equal to theta of f is equal to minus 2 pi f into t naught, which is proportional to the frequency. It's proportional to the frequency minus. It's a distortionless transmission. Understood? I'll go for the next topic. Response of linear system. Response of a linear system. In that, the first one is impulse response. Impulse response. The convolution relates input and output. The convolution relates input and output of a linear time invariant system. It is gives as y of t is equal to x of t with the convolution of h of t, and integral minus infinite to infinite x of t minus tau, h of tau d tau. Here h of t is called impulse response of the system. Impulse response of the system. See here the x of t and here the h of t. Now it is not the h of t, my dear students, y of t. Something went wrong here. It is y of t. It's a linear time invariant system, h of t and the x of t. The y of t, the response y of t is equal to x of t with the convolution of h of t. Okay, we know the convolution formula, integral minus infinite to infinite. Either you can write it as x of tau. It is also equivalent to the same, minus infinite to infinite. X of tau, h of t minus tau is also, you get the same result. Okay. Here the h of t is called impulse response of the system. It is characteristics of a particular system. Impulse response h of t of the system is obtained at the output by applying the unit impulse signal at the input. How it is the same thing. If I am taking the system, that is also linear time invariant system. Okay. Apply the delta of t here. Delta of t. You'll get the h of t with the h of t1. What I told in the previous classes, any signal is convoluted with impulse function, you'll get the same function. H of t is equal to delta of t with convolution of h of t, you'll get the same signal. Okay, it is a characteristics of a particular system. Impulse response h of t of the system is obtained at the output by applying unit impulse delta of t at input, when x of t is equal to delta of t y of t is equal to h of t. Means I change this as x of t is a delta of t. What is a y of t? H of t. Same. Impulse response. Response of the linear time system. Next one is a frequency response. Impulse response, and then next one is a frequency response. The frequency response analysis and differential equations, etc., can be analyzed with the help of Fourier representations. For example, the Fourier transform x of omega gives frequency spectrum of the signal. We know that the output system is y of t is equal to x of t with the convolution of h of t. Okay, in all the concepts what we discuss now, it is related with the convolution. Either it is an impulse response related is a convolution, frequency response is related with the convolution, and previously we discussed about the frequency response of the linear time invariant system with the distortionless transmission. Okay, it is also related with the convolution. Understood, my understood. The frequency response analysis and the differential equations, etc., can be analyzed with the help of Fourier represents. For example, the Fourier transform x of omega gives frequency spectrum of the signal. We know that the output system is y of t is a convolution of x of t and h of t. Apply the Fourier transform, y of omega is equal to x of omega into h of omega. What is the transfer function? H of omega is equal to the output to y of omega, the input to x of omega. Okay, my dear students. It's a frequency response. You see, by convolution theorem, the above equation becomes y of omega is equal to x of omega, h of omega, or y of f is equal to x of f into h of f. For this function, you can apply the Fourier transformation. Okay, my students. So, what is the inverse Fourier transformation? The above equation y of t is equal to inverse Fourier transform of x of omega into h of omega. Thus, the output y of t can be obtained by taking the inverse Fourier transformation of the product of x of omega. Let us now study these concepts. The convolution is given as y of t is equal to integral minus infinite to infinite h of tau, x of t minus tau d tau. Let the input be e power j omega t, that is a sinusoidal or the sinusoidal. And the above equation becomes, it is the input, my dear students, x of t is equal to, what they are assuming that, let x of t is equal to input e power, not the minus, it is a plus only, my dear students, j omega t. Now I can substitute in this equation y of t is equal to integral minus infinite to infinite h of tau. What is the x of t? E power j omega t. But here x of t minus tau, instead of t minus tau, instead of t there is a t minus tau. So e power j omega into t minus tau. Why? The t is replaced with the t minus tau, my dear students. Okay. That is equal to integral minus infinite to infinite h of tau. Now you can split this exponential as a two parts, e power minus j omega tau and e power j omega t. Okay, my dear students. So what is this equation? Fourier transformation of the h. Okay, the y of t is equal to, is a Fourier transformation formula, the h of omega into e power j omega t. The above equation, the integral represents the Fourier transformation of h of tau, that is y of t is equal to e power j omega t h of omega. Here the h of omega is a Fourier transform of the h of t. The above equation shows that the output y of t contains the same signal as input e power j omega t. The output is also having e power j omega t multiplied by the h of omega. Okay, what we assume here, x of t is equal to e power j omega t, nothing but it is the input. What is the output we got? Y of t is equal to e power j omega t, but it is multiplied with the h of omega. Okay, my dear, here the h of omega is a Fourier transform of h of t. The Ibo equation shows that the output y of tau contains the same signal as the input e power j omega t multiplied by h of omega. This h of omega is called frequency response of the system. It is also called as transfer function of the system. The another one is the frequency response of the system. Remember, my dear students, what is a h of omega or h of f? We can call it as frequency response of the system. Frequency response of the system. In some examples, if they ask to find out the frequency response of the system, means how to find out h of f or the h of omega. Okay, my dear students. So you can also call it as a transfer function. Transfer function. Both the functions is the same. Either we can call it as frequency response of the system or transfer function of the system. Okay. So the y of t is equal to h of omega is a frequency response of the system. Again, consider the convolution y of t, h of t with the convolution with x of t. By convolution property of the Fourier transform, y of omega is equal to x of omega, h of omega, or y of f is equal to x of f or h of f. Now the transfer function h of omega is equal to y of omega by x of omega. Here h of omega represents the frequency response of the linear time invariant continuous time system. These functions are also called as system transfer function. I told that it is a h of omega, we can call it as frequency response of the system or system transfer function of the system. Okay, system transfer function or frequency response of the system, both for the h of f only. H of f or h of omega. Understood, my dear students? We discussed the frequency responses of the linear time invariant systems. The two functions. One is impulse response, another one is a frequency response. What is a frequency response? H of omega is equal to y of omega by x of omega. Now you can see the one other example of the frequency response. The impulse response of the continuous time system is given as impulse response, nothing but h of t. Remember, these are the words, the technical words in the signals and systems. Impulse signal is a delta of t. Impulse response is h of t. Remember, my dear students, impulse response is h of t. Impulse signal is a delta of t. So given it is an impulse response, h of t is equal to 1 by RC power minus t by RC mu of t. Determine the frequency response. Nothing but you have to find out the h of omega or h of f and plot the magnitude and the phase. Okay, magnitude plot and the phase plot. Take the Fourier transformation of the given impulse response. H of t is equal to h of omega, that is integral minus infinite to infinite h of t e power minus j omega t dt. Given the h of t, you can substitute here. This is a h of t 1 by RC e power minus t by RC mu of t e power minus j omega t in dt as a definition of the Fourier transform. Next, take the 1 by RC is a common. Here the mu of t, it can varies only from 0 to infinite, as the magnitude is a 1 for the t variables mu of t. So change this as a, keeping that it is a mu of t is a 1, and change the limitations from minus infinite to infinite is a 0 to infinite. So e power minus t by RC, e power minus j omega t dt. So 1 by RC integral 0 to infinite, both the bases are the same. You can add the powers. Take the minus t is a common, j omega plus 1 by RC into dt. Apply the integral of exponential value, e power minus t, j omega plus 1 by RC, and keeping there is a t coefficient as in the denominator, 1 by j omega plus 1 by RC and the minus. Substitute the upper limit, it becomes of 0. Lower limit is a 1, and that minus value and minus value becomes of the plus 1 by RC in the denominator and numerator, and denominator also j omega plus 1 by RC. That is equal to, we can take the RC is a multiplied here, see, 1 by RC whole divided by j omega plus 1 by RC. Okay, my dear students. Now cross multiply here, 1 by RC whole divided by j omega RC plus 1 by RC. So RC get cancelled. Finally, it becomes of 1 by 1 plus j omega RC is the final equation. H of omega is equal to we got 1 by 1 plus j omega RC. What they are asking, you have to find the frequency response, nothing but this is a frequency response only. Frequency response. And also plotted the magnitude and the phase. To plot the magnitude and phase, you can multiply with 1 minus j omega RC by 1 minus j omega RC. Numerator is 1 minus j omega RC whole divided by 1 plus a plus b into a minus b. 1 minus j omega RC whole square, a square minus b square. What is the j square is nothing but minus 1. Here already minus is there. 1 minus j omega RC by 1 plus omega RC whole square. Now what is the real term here? For the frequency response, h of omega is equal to 1 by 1 plus omega RC whole square minus j into omega RC by 1 plus omega RC whole square. And what is the magnitude of this one? H of omega, you can take it as a magnitude under root of real square and imaginary square. What is a real square here? 1 by 1 plus omega RC square and the whole square plus, and the imaginary coefficient square also, omega RC by 1 plus omega RC whole square and whole square. Now take the LCM is the same here, 1 plus omega RC whole square. Numerator is both are same, 1 plus omega RC whole square whole divided by 1 plus omega RC whole square and whole square under root. So here the one term is there, and take the square of the term. Therefore, h of omega, the magnitude is becomes of 1 by under root of 1 plus omega RC whole square. Magnitude. Now what is the phase? The angle h of omega is equal to imaginary coefficient tan inverse, because it is in the x minus jy. X is a positive and imaginary coefficient is a negative, means the fourth quadrant. Fourth quadrant is a minus tan inverse y by x. What is the y here? Omega RC. Denominator is the same for both, 1. Omega RC by 1. Now using the omega, the values, we can plot the magnitude and the phase. Okay, my dear students. See here, 1 by 1 plus j omega RC into 1 minus j, 1 minus j. Simplify this equation. The magnitude we got 1 by under root of 1 plus omega RC whole square. And angle is minus tan inverse omega RC. When RC is equal to 1, let RC is equal to 1, the magnitude and the phase responses will be, what is the magnitude here? RC is equal to 1, what is the 1 by under root of 1 plus omega RC? And the phase, see the phase becomes of RC is equal to 1, the angle it is, angle h of omega is equal to, RC is equal to 1 means tan inverse minus tan inverse omega. So take the omega is equal to 0. What is the omega is equal to 0? The magnitude of h of omega is equal to 1. And angle h of omega is equal to minus tan inverse 0 is 0. Okay, my dear students. And what is the omega is equal to minus infinite? Minus infinite, what is the magnitude h of omega? Here the infinite, my dear students. 1 plus infinite is a infinite only. 1 by infinite becomes 0. What is an angle? Tan inverse infinite. Minus infinite actually, my dear students. Tan inverse of minus infinite. That is a minus of minus, tan inverse is a plus, we will be getting. Tan inverse infinite, angle of h of omega is equal to pi by 2. Okay, that is a minus infinite. Let us see the omega is equal to infinite. Again, the h of omega is equal to magnitude is a 0. Because here the 1 by 1 plus omega is a infinite, is a 0. 1 by infinite is nothing but the 0. What is an angle here? Angle of h of omega is equal to, now it's a plus infinite, tan inverse infinite is a 90 and minus, so minus pi by 2. So we got, and omega is equal to 0, the magnitude is a 1 and angle is a 0. And omega is equal to infinite, so magnitude is a 0 and the angle is a minus pi by 2, the pi by 2 is a variable. Okay, my dear students. Now you can see the plot here at omega is equal to 0. See the frequency, x-axis, we take the omega. At omega is equal to 0. See, this is the value is a 0. What is the magnitude? We got 1. And omega is equal to infinite. What is the infinite? 0. Becomes of 0 here. What is the infinite? Minus infinite. Minus infinite is also 0. The magnitude plot is a magnitude plot. And phase plot, coming to the phase plot, omega is equal to 0. What is an angle here? 0, my dear students. Here the 0, angle is 0. Omega is equal to, and omega is equal to minus infinite. What is the angle here? The pi by 2, plus pi by 2. See the plus pi by 2 here. This is a plus pi by 2, my dear students. Plus pi by 2 the angle. And omega is equal to infinite. See here the omega is equal to infinite. And here the minus omega, minus infinite. What is the value? Omega is equal to infinite. The angle is a minus pi by 2. So see the minus pi by 2 here. Up to this is a minus pi by 2. So the curve varies from minus infinite to crossing to the 0 and goes to the plus pi by 2. A plus pi would start the plus pi by 2 and crosses the 0 and ends at the minus pi by 2. We got the magnitude plot, and this one is a phase plot, my students. Phase plot. Understood? It's a very, very important. Is one of the example in the mid examination also, my students. If suppose if any mid examination will conducted, definitely this is a mid exam question. Remember that one and note down also. All right. See the explanation part here in this figure. They observe that the magnitude response is a symmetric. Why it is a symmetric? In the positive relaxes is monotonically decreases, and negative relaxes also monotonically decreases. So you see here the magnitude response is monotonically decreasing, as this is a low pass filter. Low pass filter. Call it as a low pass filter. Low pass filter means it allows only the low frequency value. This is a positive. And similarly, when you take the low pass here, the negative relax is also like this. But the phase response is anti-symmetrical. So here it is a positive value, here it is a negative value. This is a symmetrical. Both the positive and negative is the same, but anti-symmetric means positive and negative values is positive values and positive values is the negative angles. Understood, my dear students? It's a very, very important. Remember, my dear students, in the winter examinations also, definitely I'll give this question. As this is a low pass filter, magnitude plot. Coming to the next example, the system produces the output of y of t, e power minus t mu of t for an input of x of t is equal to e power minus 2t mu of t. Remind the impulse response. Impulse response means h of t. Frequency response means h of f. Remember, my dear students. Impulse response is h of t. Frequency response means h of f. Given the output function and the input function. Output function is e power minus t mu of t. Input function is e power minus t mu of t. We already know that e power minus a t mu of t Fourier transformation is 1 by a plus j omega. What is the a here for the y? Y of omega is equal to, it is a 1. So 1 by 1 plus j omega. For the x, what is the a here? 2. X of omega is equal to 1 by 2 plus j omega. So to find the frequency response or the transfer function, the system transfer function, h of omega is equal to the ratio between of y of omega and x of omega. Keeping this y of omega as 1 by 1 plus j omega whole divided by x of omega is 1 by 2 plus j omega. Cross multiply, numerator and the denominator is interchanges. 2 plus j omega by 1 plus j omega. This h of omega is equal. Okay, my dear students. We got the frequency response. Now you can find the h of t. H of t means inverse Fourier transformation of this function. Inverse Fourier transformation. So what is the inverse Fourier transformation? You can split this into two parts. See the next part here. H of omega is equal to 1 by this 1 by 2 plus j omega by 1 plus j omega. The h of omega is equal to, you can write it as two parts. Either using this all the things, no need of this all the things, you can do this, my dear students. You write it as 2 by 1 plus j omega by 1 plus j omega. It is somewhat difficult to write into the inverse Fourier transform. What is it? 2 here? 2 is nothing but 1 plus 1. Okay, the 2. H of omega we got here only. Here itself, h of omega we got as 2. I am writing as a 2 is 1 plus j omega whole divided by 1 plus j omega. Now I am writing the 1 by 1 plus j omega plus 1 plus j omega by 1 plus j omega. It becomes of get cancelled. So 1 plus 1 by 1 plus j omega. H of omega is equal to. Now you can apply the inverse Fourier transformation of h of omega is h of t. What is the Fourier transformation of 1? 2 pi delta of omega. 1 Fourier transformation, my dear students. Inverse Fourier transformation, I am not Fourier transformation, sorry. H of omega is equal to, we got as h of omega is equal to as of inverse Fourier transformation, not the Fourier transformation, inverse Fourier transformation. H of omega is a h of t is equal to 1 with inverse Fourier transformation is a delta of t plus Inverse Fourier transformation of this is a 1 by 1 plus a plus j omega. So e power minus t mu of t as an impulse response. You see, we got this same function. H of t is equal to delta of t e power minus t mu of t. So no need to do the rationalization and simplification of this. It's simple, we got it is a 1 plus 1. Here also, h of omega is equal to 1 plus j omega plus 1. 1 by 1 plus j omega. Otherwise, it is a somewhat easy here, but otherwise you have to follow this rule only. Rationalize and separate the real term and the imaginary term, then you can apply. Here the magnitude will get and the phase also. To find the impulse response, h of t, take that is a 1 plus j omega plus 1. 1, the inverse Fourier transformation is delta. 1 by 1 plus j omega is e power minus t mu of t. Okay, my dear students. This is a very important example, sir. These two. H of t is equal to 1 by RC e power minus t by RC mu of t. Other example is, given the output signal and the input signals, you have to find out the impulse response and the frequency response. H of t and H of f. Okay, my dear students. The next topic is ideal low pass filter. In the tomorrow class, we can discuss about this as a new topic, ideal low pass filter, and other ideal low pass filters such as high pass filter and the band pass filter. With this half part of the fourth unit is also completed, my dear students. And some examples are there. We can solve in the coming classes. Okay. But what are the topics we covered now? Today's class, the frequency response of the linear time invariant system, the frequency response. In that, the first topic is a distortionless transmission through the system. Distortionless transmission through the system. The phase angle is minus 2 pi f into t naught, and the magnitude is a k. It is not independent of, it is independent of the frequency. But dependent of the frequency is a phase angle only. There is no changes occurs in the magnitude, nothing but amplitude. Another topic is the responses of the linear system, impulse response h of t and frequency response h of f. And some examples. For example, I told is a very important and definitely will get in the mid examination, my dear students. It is the first mid examination. Definite question it is. H of t is equal to 1 by RC power minus t by RC mu of t, and you have to plot the magnitude and the phase plot also. Note down this one. And another example, the y of t is equal to e power minus t mu of t, and x of t is equal to e power minus t 2t mu of t, and you have to find out the h of t and frequency response h of f. Okay, my dear students. Any doubts is there in this? The tomorrow class, we can conclude half part of the fourth unit. The fourth unit for the AAA students, and this is for the third unit. Third unit only the third unit for the ECE students. Some examples are there. Only the concepts is completed. Except examples we can solve in the coming classes. Okay, my dear students. Any doubts? Okay, thank you.